Jose. It's really my honor to chair these morning sessions. And we get to start off with Vijay Balasubramaniam from Penn. Based on his comments last night, I think we're all on the edge of our seats for what he's come up with.
I hope not. Anyway, so great. Thank you very much for inviting me to this lovely conference, and especially the organizers, because I really have to say, I just learned so much because almost every single talk was outside my field of expertise. So probably one of the best conferences I've been to in a very long time. Okay, so the conference is dedicated to physical systems that learn. And today I want to talk about sort of the reverse, the physical effects of learning. You'll see what I want to mean by that in a few minutes. This is based entirely on work with, or largely on work with Menachem Stern, Naki Stern. Naki, where are you? Naki and Andrea Liu, who's over there. How do I do that? Like this? Is this better? Is this better?
Yeah.
All right, great. So it's based on work with them. Actually, I learned everything I know about the subject from Naki here, and Naki is going to be joining AMOLF as a faculty member next year. So I'm really grateful to him, especially for teaching me everything I know here. Okay, great. So before I start, and especially because of the session last night, I want to first talk about a paradigmatic physical learning network, because we've used the words neurons and brains all over the place. My plan is I'm going to talk about what the real brain is like if you're a neuroscientist, extract from that discussion 3 facts that puzzle people, and then build a rather trivial model of the brain, but an interesting model of physical learning, and then study what learning does to that physical system. Me, it's really inspired by thinking about what the brain does. So our paradigmatic physical learning network is the brain. And as everybody here knows, the brain is made of neurons. The neurons are specialized cells, specialized in shape, to make connections and make little circuits, and specialized in their physiology, communicate and compute. They really are electrical circuit elements. You have a baseline potential of minus 70 millivolts, stick current into them, and if you reach some critical value, they go kaboom, and fire a voltage spike, come back to baseline, and keep going. In that sense, they're a digital element. At least the spiking neurons are digital elements. We've made a lot of the fact that the brain is very cheap compared to a computer. Indeed, it's about 20 watts of power compared to 80 watts from a laptop. I'd like to mention that the brain, although 2% of your body weight, is actually 20% of your metabolic load. Namely, it's 10 times more expensive than muscle. This is seriously expensive tissue. And in fact, a great deal of my work has been devoted to the idea the fact that it's so expensive is an important constraint. And therefore, the circuits are selected for either over evolutionary time or through learning for efficiencies of various kinds, in particular energy efficiency, and therefore we can learn from them about how to design some circuits. It's actually because it's expensive, not because it's cheap. Okay. So having said that, of course, you can't write poetry and things with single neurons. So what you do is you build a whole brain. This is a picture of your brain, and the surface of it, really. It's the cortex. We're very proud of the cortex, but most of the brain isn't the cortex, in the cerebral cortex. But anyway, look at the cerebral cortex. And the thing that we've known since the Egyptians, actually, is that this is not a generalized neural network or a generalized physical network, lots of identical nodes connecting to each other in this kind of very general sort of broadcast kind of way. It just isn't like that. Instead, you've got various regions, like the prefrontal cortex here does things associated with planning and personality. Back here is your visual cortex. If you bump it, you start seeing stars, like in the cartoons, because you have, a bruise on the circuits. And in the middle here, there's the motor cortex, which you use to control your body. But if you look at that, so, computational functions therefore distributed across the brain, but segregated in a particular way. On the other hand, if you look at any one of these regions, it's further segregated. For example, the circuits here control your face, and the circuits at the top here control your knee. This is why if you happen to have a stroke right here, left side of your face will sag. Well, the right side of your face will sag because there's a crossover. So it's very specific where the circuits are. It is not all-to-all connected general purpose machine of that kind. These are lots of specialized circuits, different kinds that have been selected to do what the things they do. I'm emphasizing this. It's very different in character from many of the things we've discussed over the last week. Now, furthermore, these regions are organized in complex interacting networks that you could draw an analogy with actually the wiring diagrams you get in silicon. For example, if you're an animal, a critical function for you is to be able to map the world and move. If we didn't map the world and navigate and move, we'd be plants. So you have to do that. And so, of course, you dedicate circuits in your brain to do that. And there are many areas of the brain involved. One is the hippocampus. And in the hippocampus, you have various sub-areas, CA1, CA2, CA3, the dentate gyrus, etc., which do various kinds of memory, planning, mapping, pattern separation, completion, things of this kind. You get inputs into this region from another region called the entorhinal cortex, which has a left part and right part. Well, a lateral part and a medial part. And the lateral part does things like identify events and where things are and what is it. And the medial part identifies where you are in the space. It's got circuits dedicated to that. To do all of that, of course, you need sensory input and motion input. So there are further regions, perirhinal and postrhinal cortex, subiculum, many other areas that are charged with gathering that information from the sensory periphery, formatting it correctly, and sending it in. This looks like a complicated wiring diagram that you might put together in a silicon circuit. Again, this is not an all-to-all connected general purpose, all the units are the same kind of thing. I'm just trying to emphasize the differences between what most of us have been thinking about. In particular, if you look at these, open these things up, there is a zoo of cell types. For example, there are border cells, boundary vector cells, head direction cells, speed cells, place cells, landmark cells, object vector cells, egocentric cells, telling you where things are relative to self, allocentric cells, cells that tell you where things are relative to an absolute landmark. I mean, there is a total zoo here. That is also not like most of the networks we've been building. All these specialized units and specialized things. To drill that down, here's a 100-year-old picture of the retina drawn by Ramon y Cajal, Santiago Ramon y Cajal, essentially the founder of modern neuroscience. Gorgeous, gorgeous drawings. He drew a picture like this of the retina, with the photoreceptors feeding into 10 types of what are called bipolar cells, feeding into 10 types of what are called ganglion cells. The ganglion cells, they're outputs of the optic nerve. These things, make up basically the feature detectors that pull out features of the visual world. Now, with 100 years of experience in modern techniques, we now know that this was even a cartoon, Al's picture is a cartoon. There are 60 types of cells in the retina alone. And look, they all look different from each other. These are the so-called amacrine cells. They're inhibitory neurons that are the computational engines of the eye. And he completely missed them here. And these amacrine cells, look at how many different shapes there are. In biology, there's a general rule that form follows function. You can probably bet they're doing different things. And indeed, you can go measure from them, and they all do different things, right? So the circuit, if you want to understand these circuits, you really have to contend with this kind of detail. Personally, one of my research questions is to ask, why is there more than one kind of cell? Because you could build an arbitrary circuit from a NAND gate. So what drove evolution to produce this heterogeneity? So, I've written a substantial number of papers that this kind of structural heterogeneity is directly responsible for the computational resource efficiency of computation in the brain. You can make various arguments about that. If you're interested, you can look in this article in the proceedings of the IEEE for one little piece of that class of arguments. Hakan, you had a question, I think.
I would just want, cells, how do you classify? Can they be?
Excellent. So there are various modes of classification. One is the basic thing is structure. You look at them, they look different. They may be the same kind of cell that's sort of branched a little bit differently. Then you can look at their gene expression patterns, the transcriptome, their biochemistry. They'll express different receptors. They'll express different kinds of neurotransmitters.
So they are well-defined classes. There's other cases.
The universe is full of lumpers and splitters. Lumpers will look at a distribution that looks like this. Say it's the same distribution, a little bit of lumpiness. Splitters will say clearly there are two types. In life, what will happen when you look at this data is you'll find a nice lump here and a nice lump here. And there's something that is hard to understand in between. Now, whether you say that was a mistake made in the middle, or whether that's an intermediate that's there, perhaps as a substrate for future evolution of new types, it's not clear.
So it's a spread. It's a distribution of.
You are a lumper. My mentor into this field, Peter Sterling, who was a neuroanatomist, was definitely a splitter. Professor Masland here is definitely a splitter. Right. So the more fulsome statement here is that there are clearly very well-defined lumps, but there are in the valleys between them you will find intermediates. And read that the way you will. Okay, great, wonderful. So again, this is, I'm again trying to make a contrast the circuits that I will talk about in about 5 minutes. Go further, this is not even a static architecture. So these are regions of the brain associated with language. There's Broca's area, which you use to produce language. There's a Wernicke's area, which you use to comprehend language. So for example, if you damage Broca's area, you can't produce speech anymore. You can understand it. If you damage Wernicke's area, you find that you can produce perfectly good speech. It just doesn't make any sense, right? Semantics and syntax is sort of production are kind of separated. Then there's this kind of area called Gershwin's area for concepts. So, people used to think there's Broca's area and Wernicke's area, speech understanding versus speech. And later, as the century passed, people understood, well, it's more like they connect with each other, they communicate. Today, with all the techniques that fMRI and so on, we understand there are other areas like motor areas and other areas involved, that these areas flexibly reorganize the circuit, right? Who talks to who and how changes depending on what you want to do. So it's an extremely dynamic structure, even in its functional connectivity. Again, I'm trying to contrast with what I'm going to talk about in 5 minutes, right? Make it very clear that if you talk to a neuroscientist, this is what they're thinking about. Okay? So now, what about learning, which is what we're interested in? So one thing that is true, and which is relevant for the kinds of interests that we've had, is that neurons learn by autonomously rewiring their own circuits, and they do this based on local rules. There are various local rules that have been measured by the biologists. One such rule is spike timing dependent plasticity. And the way that would go is that here are 2 neurons. Let's suppose one fires before 2, maybe the synapse strengthens. If one fires after 2, maybe the synapse weakens. So it's a temporal rule for rewiring the circuit. And this is some paper by Mahaffey and Dupe in zebrafinch showing a particular synapse where they found this sort of rule. It's actually shifted a little bit, 0 time lag. So that's a sort of local rule. Neuron doesn't know anything about anything, doesn't know anything about your task. It's just looking for what went first. There are also some global knobs, but they're very coarse. So for example, the neuromodulators. The neuromodulators are things like dopamine. Something good happened, boom, chuck out a little spritz of dopamine. And then, all the neural circuits know, I don't know, whatever I did the last time, maybe it was good. Something good happened. At that level of coarseness. There are things like norepinephrine, which is another neuromodulator that allows you to affect synaptic plasticity, right? In any learning rule you write down by hand, it's the rate of learning, right? There's a learning rate. You can tune that neurons by dumping norepinephrine or not. You're primed to change the synapse or not. So there are sort of global knobs of this kind, but it's not very, very specific. So an individual neuron or synapse has no direct knowledge of how the other neurons in this ghastly network or beautiful network, depending upon your point of view, are reorganizing themselves in order to perform the task that he wants. So it's really local in this kind of way. So despite that, learning requires whole brain cooperation in all these crazy areas. For example, if you're a baby songbird trying to learn a song, 3 key areas that you need to use in your brain are called RA, HVC, LMAN, never mind what the acronyms mean. So HVC here is kind of like a conductor. It produces sort of patterns of neural firing that keep time in the song. The goal of the bird is, depending on what pattern it sees, it needs to use RA, control its muscles, to produce the right sound, like its parental song. Unfortunately, there's a credit assignment problem, and baby bird doesn't know which neurons are attached to which muscle. They got to figure this out in order to be able to play the song. Then there's another area called LMAN, which is the tutor area. And it injects both variability, some noise, some exploration that RA can do, that the student can do. It helps the student explore, and it provides little guidance like, oh, that was kind of overall good. This combination of things winds up producing birds that can learn beautiful songs, their parents. Right? It's a local synaptic plasticity and some sort of vague global guidance of jitter a bit, and oh, that was good, roughly speaking. That's how learning works. Okay? So when you learn in this way, in this amazing distributed and extremely heterogeneous structure, you find that there are actual physical effects of learning in the brain. And everybody knows about, has heard about London cab drivers back in the day before GPS. having larger areas of the brain associated with making maps of the world, right? Like their hippocampus. Teenagers apparently have enlarged areas in their head associated with thumbs, because that's associated with texting and violinists and so on. People say stuff like this, and it's sort of true. But in a very real sense, even from that anecdotal example, you kind of become what you learn. And that's because synaptic connectivity, the circuits, reorganize with learning. They just become different. Okay? So there are many, many structural effects of learning, which today I wish to highlight two are often mysterious to neuroscientists. So one thing that's mysterious often is you'll go to some cortical area, it has like 1 million neurons and probably 10 million parameters, maybe 100 million parameters, and then you'll learn your task. You'll find that if you record from this region of the brain, it appears that all the responses are on some low-dimensional manifold, right? And then it'll be different manifold for different tasks. There's some low dimensionality to it. And when you look again and again, in other ways too, you have to do some task. You could have done it with 85 cell types, but instead you seem to have the minimal number of types of cells or feature detectors or whatever else that's necessary to do the task. Another thing that's interesting and that you keep noticing again and again, both experimentally and using theories like information optimization in the brain, is that the response repertoires of circuits in the brain aligned with both the features of the inputs you're interested in and the desired output. So there's an alignment with the task and the world. In a real way, you're becoming what you learn, right, inside the head. That's how the circuits are organized. The mystery, so that's been observed, and you can also prove why you want that by having theories of things like efficient computation and communication. You say, I have a resource-limited computational engine, and I need to, put my money to bits of circuit, can do the job as quickly as you can, with as few neurons as you can, with as little ATP, burning as you can, etc. And you'll conclude that you ought to structure circuit in this way. So there are, to say, normative theories of why the circuit should be structured this way. But the question, how do local learning rules, synapses, manage to produce these effects? There's somehow a global coordination you need in order to produce this effect. Okay, so that's a question that neuroscientists and theorists, even theorists in the field, and even experimentalists in the field, really know the answer to and would love to have some insight into. So we're going to try to address this question using the following strategy. And so here, I'm reflecting one of the comments that was made, I think, by Eric Winfrey, by Thierry Mora yesterday, that we can use this kind of computational thinking as a kind of lens that will help us to understand other systems, as opposed to, to build new systems. I'm going to use it as a lens and see what I get. The strategy is the, time-worn strategy, the rogue and the physicist, which is you really want to solve this hard problem, you don't know how to do it, you'll construct a pared-down pretend problem with minimal features of real neural networks that you think may be relevant and that which can learn, and we'll see if it develops the same structural adaptations as seen in the brain. So the idea here is, of course, to try to extract the minimal features in the system, achieve the effect that you want, and then you can add the bells and whistles and other things. Sometimes it's a very good strategy, sometimes it stinks, and there's a little bit of an art figuring out when you're in one regime versus the other. I'll try to convince you that this is a good setting. Okay, here we go. Here's our class of tractable physical models. It's like a ball and spring network. Now, you show this to a neuroscientist, and they will start laughing uproariously. Because you know what? This doesn't look anything like what we talked about before. But actually, that's too quick. You can start with an actual neural network, model it, if you like, as baroquely as you want, with the Hodgkin-Huxley equation, fancy lots of neurotransmitters, etc. Coarse grain it a little bit, and say, I'm not interested in all the fine details, and you could write down some effective model like the so-called Izikevich model. Then you can coarse grain that a little bit also and say, I'm not really interested in all the details of the spikes, I just want the firing rates. And you might arrive at something a little bit coarser, like the integrate and fire model of Lapique. Wrote it down, 1907, same year as special relativity. Right? So you write that down, and you construct a network from that, and you start calculating. You say, well, suppose I consider that the time scale for relaxation of the circuit is shorter than the time scale at which I'm going to present signals to react to and learn. And then you can get rid of all of the dynamics, and eventually you will arrive at something that's a little bit like this. The cartoon, there's a pathway to this cartoon from the full thing. Okay? So I just want to justify that. Anyhow, what's our cartoon? We imagine some physical system which consists of some physical degrees of freedom, which I'm drawing here as nodes, which are interacting via some learning degrees of freedom. You should think about this like the neurons, and here are the synapses connecting them through the axons and dendrites. And we imagine that the way we kick this is by applying a force to it, apply forces to these things. And there's a sense in which when you provide a voltage kick or a current kick to a neuron, you're providing a kick to it, the dynamical system sense. We're going to cartoonize that in this way. And we're going to imagine that it starts off at rest. That rest means whatever the equilibrium state is. You well know, so I'm going to describe that equilibrium by an energy function. The x naught is the rest state. And as you know, around equilibrium, you can always make any energy function quadratic because the linear term will vanish. Here's our quadratic piece. And this thing here is the physical Hessian. We're going to consider a very general class of physical Hessians, which have the following character. Phi here is a pointwise nonlinearity. So it's a nonlinear function of, if you like, the synaptic weight or the edge weight. And we have here a left matrix and a right matrix. And I'll give you a better sense of what those things are in a minute, but they're really supposed to encapsulate structure, the physical structure, what's connected to what on the network. I'll give you an example in a minute, so then it'll be clear. And then what do forces do? Well, you can describe the effect of a force, saying you push, and the effect of a push is to add a term like this, F dot X, to the energy, that's because that's the tension you'll produce. Then if you take the derivative, it'll tell you that the gradient of the energy should be equal to the force. Standard, dynamical rule we would write down. So this is your basic response. The thing I want to point out is notice this free state that you get by pushing the thing minus the rest state is the inverse Hessian of the force. The reason that's important is it tells you why effects in such networks are totally non-local. Right? The inverse, the entries of the inverse of a matrix, functions of every entry in the original matrix. You cannot look edgewise to tell me what's going to happen. It's a global effect, the thing that happens. That is what makes all learning and dynamics with networks so difficult. It's this property. Okay, here are some examples. This is basically a linear network. It has sort of XHX with H being some symmetric matrix as its Hessian. By the way, one way in which this is different from neurons, which I forgot to mention, is in neural circuits, usually the connections don't have to be symmetric. So we're talking about a symmetric system that makes it easier because the eigenvalues are going to be real, stuff like that. So one of the things we are thinking about how to make this non-symmetric and keep going, but I'm going to do symmetric networks today. There are flow networks that have been talked about extensively in this meeting, as well as mechanical networks, and those have energies that look like, X is the position, X naught is the baseline position, the mechanical network. There's a Hessian here, and this Hessian you can write as the diagonal set of weights. No way. All right, I'm gonna go through my question time. Okay, you can't ask me any questions. There's diagonal weights. The problem was the discussion yesterday, because I felt obliged to say what a brain actually was. Okay, so there's the diagonal weights, and then you multiply it on the two sides by this kind of incidence matrix, and that makes the correct Hessian. Okay, so what is the effect of forces? Well, you kick it, and as I said, you get this free state minus X naught will be the inverse Hessian times F. And way we're going to do the computation, quote unquote, and the learning is you pick some input nodes, apply forces there. You pick some output nodes and measure their deviation. And an example task is allostery, where what you want to do is you push some nodes and you wish some other nodes somewhere else to move, maybe some other nodes not to move. That's your goal. All right, so what's the learning protocol? Fortunately, because so much has been said in this meeting, I don't actually have to tell you the details. We're going to use Cellier and Bengio's contrastive learning approach. It's been said many times. I'm going to repeat this quickly. The way this goes is you have a cost function that, let's say, tells you that is some measure, some positive measures, maybe some quadratic measure of deviation of the response and what you really wanted. That's this thing here. Then what you do is you say, I have the physical system, did what it did. I know what I wanted it to do. You push it in that direction. And you measure the energy of the system in these two states, measure the energy after pushing and before pushing. You take the difference and you take a gradient of that. that will guide you along the right path to learning. I'm not going to repeat why this is the case because it's been discussed, fulsomely in this meeting already. We're going to do that. The first statement with these networks, this works. So we'll do allostery, start with some node, imagine some other node should move in some way, pick random forces, train and see what happens. Just to check, this is the sanity check that this works. And indeed it works, the error tanks. This is only one task, it's not a hard task. Just checking that you can learn. Okay, so the error tanks in all of these kinds of networks. You can do this for other kinds of tasks. Now, I am interested in the structural changes to the network that happen because of the learning, because I want to see if it gives me some insight into the neural circuit. What I want to know is how this Hessian changes. With a little bit of work, you can demonstrate that the learning rule applies this equation, the change in the network weight. You can imagine what this is. Take some derivatives, do some chain rules, put them together. I'm not going to bore you by doing that for you on the board. That's what you do. Then, okay, fine. Now what do you need to do? You need to propagate this into the change of the Hessian, because the Hessian is a function of the weights in two ways, explicitly, and also implicitly in terms of the ground state of the system. You propagate it through and do, again, more chain rules, etc. So here's the result. Okay? So we're going to take a linearized task, because we're going to assume everything is weak forces. That's easiest to do. We're going to assume the initial network is random. And because the initial network is random, there are various things that will average to 0. And then we use the chain rule. Okay? And then what we're going to do is to ask how the eigenvalues and the eigenvectors change in first-order perturbation theory. We can go to higher orders too, but if the forces are weak, we can stop at first order. And here's what you find. You get these two equations. And y and x, which I have not written down here, sort of structural tensors associated with the geometry of the network. I'll give you an example in a minute. It'll make this easier to digest because those tensors won't be there. You notice various things. The changes in the eigenvalues and in the eigenvectors are larger for those eigenvalues that are small. But the eigenvalues, the changes drive them to be smaller. That's the minus sign here. If the F and I should tell you what F and A are. F and A are the forces in the output task, the task and the input projected onto the eigenvector space. So if the task and the output are both aligned with your eigenvector, then the eigenvalue will go down. Whichever eigenvector randomly that started with was most aligned with both of them is going to go down most. Right? And that's going to get put down. It's hard to digest, so let's do an example. If you do the example of this kind of linear network, this is easier to see. You see the change in the eigenvalues goes as 1 over the eigenvalue to the 4th. So the inverse eigenvalue, you can see in all these cases, you've learned one task, inverse eigenvalue goes up. This is, and here, this is a measure of alignment of the eigenvector, the task and the output, and the measure of alignment also goes up. I won't describe why this quantity is the measure of alignment. In this literal way, network has become what it learned. I'm almost done. I'm going to finish with the minutes. Excellent. Then I can show 2 slides. First is, so let me formalize what I just said. This network becomes soft and low dimensional. The way you can test that is you kick it with the random forces and let's see what it does. You can write down a measure of the effective conductance, the give of the network, the effective dimension. This is basically a participation ratio dimension. And you can see that the networks become softer and they become low dimensional, their responses. And for linear networks, so the formula are the easiest, you see how the dependence on the eigenvalues goes, so that you're dominated by the lowest eigenvalues. The lowest eigenvalues, you already said, are getting driven lower and lower and lower. That's how you get this low dimensional thing. One more fact, and then we're done. What happens if you train multiple tasks? So far, I've been doing the easy case of one task. Here's what happens. Multiple eigenvalues start to get soft. Not necessarily as many as the number of tasks you have. So you might think that there's all, well, I don't know, you learn a task, get one eigenvector, you learn a second task, you get a second eigenvector. You go like this until you run out of eigenvectors. That's not the way this works because of the non-locality of the whole thing. So here you've learned 5 tasks, and sometimes you get 3 eigenvalues. It depends on details of the structure of the network. That's the first thing. The other interesting thing is that beyond every network has a learning capacity, which is much less than the number of nodes in the network. And beyond learning capacity, 2 things happen. The error grows, you can't really learn it. The network becomes stiff, so you look at the measure of conductance, it tanks, but it remains low dimensional. So you do some learning for a while, you get this low dimensional thing, it'll become very rigid. And that's that. So this is my conclusion. So what I've convinced you is networks like this become what they learn. The network weights reorganize with learning. Response becomes low dimensional. The responsive modes become soft and aligned input forces and the task. This is an analogy with the 3 structural things I said about actual networks in the brain. Perhaps it's providing an insight. There's a 4th thing, the beyond network capacity of networks remains low dimensional but becomes stiff. That's like taking your high school student trying to stuff too much stuff into their head, sending them to Kumon classes and what have you. They get sick and tired and say they go play baseball instead. Okay, so anyway, so this, I'm not sure what the analogy is. I'll leave you 2 comments. One is, perhaps this guides us into how you can discover what some physical network in nature has been trained for, sort of kicking it, seeing how it responds to random inputs. Interestingly, that's what neuroscientists actually do as a discovery method when they see a new circuit. They kick it with random inputs, and they see what happens, and they have techniques for reading out function from that. Second comment is it'd be really great. We already got a lot of purchase picking an absolutely minimal model, right? It would be great to include more actual features of neural circuits, like heterogeneity units, asymmetric connections, dynamics, neurogenesis, depth, things like this. But that's for another time. I'm done.
Next speaker